Greetings and welcome back. Today we'll be looking at elimination. Just like substitution, elimination has two possible mechanisms and we need to understand both of them. So in an elimination reaction, what you need is a carbon with a leaving group next to a carbon with a hydrogen. We remember that this carbon right here with a leaving group is a leaving group, and the carbon next to a leaving group is an electrophile. And anytime we have a CH next to an electrophile, it is acidic. We react this guy with a base, and what will happen is we will generate an alkene. In terms of functional group interconversions, this always starts with an alkyl halide or some type of carbon attached to a leaving group, and it always gives us an alkene. You would have then whatever your base was will have grabbed an extra hydrogen, and your leaving group will have left and be all by itself with a new minus charge. Or if it was positive in the first place, it would become neutral. All right, so this is overall what elimination looks like. Let me write that up. Elimination. We eliminate two things from our starting material, and we don't replace them with anything. So the E2 reaction looks like this. We have a CX next to a CH. We have to have a strong nucleophile, a strong base. So usually an O minus, but it is a base with a minus charge for sure. That will pull off the hydrogen. It aggressively wants to share its electrons, and the electrons holding on the hydrogen would make the pi bond, the leaving group would leave. It would be all one step. The strong base would become now a neutral molecule. Whatever the base was is attached to hydrogen, and we will have a leaving group that has left. You'll notice that this guy requires a strong base in order to pull that hydrogen off all in one step. It is a one-step reaction where the rate is equal to the rate constant, little k, times the concentration of both of those reactants since they react together. So the concentration of the base times the concentration of whatever your alkyl halide is. Because these guys are both raised to the first power and 1 plus 1 is 2, it is second order overall. Again, just like SN2, we determined this experimentally. We've also determined experimentally that an E1 reaction can occur. You remember that SN1 reaction doesn't need a strong nucleophile. Similarly, in E1 reactions, you only have usually a weak base. So it's going to be a neutral base, something like water. And it's just going to sit there. The base is not strong enough to want to pull that hydrogen off without the leaving group having already left. So the first step of E1 is actually the exact same thing as the first step of SN1. The leaving group leaves and generates a carbocation. Now you have a really strong electrophile next to a CH, and therefore, in the second step, your weak base can pull off that hydrogen right next to the electrophile. The electrons holding on the hydrogen can now be shared with the electrophile and make an alkene. All right, so this usually has a weak base, but the rate is going to depend on the slow step. And the slow step is that first step. So if we draw out our reaction energy diagrams, well, in this case, you just go from starting material to product. In this case, you start with your starting material, and you get that carbocation intermediate, which is way less stable in terms of being higher energy. And then in the second step, you would get your product. It's two steps. The rate depends on the slowest step, which is the first step, and the only reactant in the first step is the alkyl halide. This is a first order reaction, and therefore we call this E1, just like SN1. And just like SN1, there is the complication of the fact that you form a carbocation, and carbocations can possibly rearrange. And you will get a lot of possible products when you do an E1 reaction. All right, so let's jump into E2 really quickly, and then we'll move into E1. In this case, we have a leaving group, and that strong leaving group is attached to a carbon, and therefore that carbon would be an electrophile. We could have a nucleophile come in and share the electrons with the electrophile, but another thing that can happen is elimination. We will have, in elimination, we're looking for a CH directly next to your electrophile. And in this case, it happens that we have two different carbons next to our electrophile, and both of them will be a little bit acidic. Both sides, that is to say. It doesn't matter which hydrogen you pull off. NaOH is a strong base. As we know, this guy is really Na plus, OH minus, and O minus can make a very strong base. So the base can pull a hydrogen off of a neighbor, have the electrons come down and form the pi bond, and kick off the leaving group. That would give us this product right here. And I'll draw in those H's again. But we have two options. We have a second reaction that can occur, which is that your OH minus could also, this is instead, not at the same time, pull the hydrogen off of the carbon to the left. Both of those guys were acidic because they're both CHs next to your electrophile. In this case, the product you would get would have the double bond more centrally located to the molecule. So unlike SN2, which only gives you one product, E2 will often give you multiple products. We cannot choose which one we get. We just get both. However, one of them is often more stable than others, and therefore there's usually a predominant alkene product that you'll get, that is to say one in higher concentrations. And this is based on the nature of an alkene. An alkene is a carbon-carbon double bond. What's included in a double bond is both a pi and a sigma. And then those guys would have two more bonds off to the side like this. Well, looking at these two carbons, they do have a full octet. They have two electrons that are located in the pi, two in the sigma of the pi bond, or the double bond, and then they've got two coming off to the side here and two coming off to the side here. So 2, 4, 6, 8. They technically have a full octet. However, the pi electrons are not very close to those carbons. Remember that pi's are loosely held and kind of floating around in space. Think of this like money you have squirreled away somewhere. It's not really in your pocket right now, so you can't really use it. So you're a little bit deprived, just like these carbons. They've got this guy hanging out nearby, but it's not really right next to them. So in effect, those carbons don't have enough electrons. They actually act like they have little partial plus charges. Therefore, what would make those carbons more stable is to have more carbon neighbors. If you have a carbon neighbor, they can donate you electrons. If you have hydrogen neighbors, they cannot. So, what would be more stable? An alkene with more carbons nearby or less carbons nearby? So, of course, just like a carbocation, if you do not have enough electrons, what you want is more electrons. And the thing that can share electrons is carbon. So therefore, if you don't have enough electrons, like a pi bond, then what you want is to have more carbon neighbors to help you overcome that lack of electrons. So the more carbon neighbors that an alkene has, the more stable the alkene is. What we need to do is look at these alkenes and consider what is directly attached to that pi bond. Here's the pi bond right here between these two carbons, and therefore the carbon on the left has both a C and an H, the carbon on the right has both a C and an H. We would say that that is disubstituted because that alkene has two carbons attached to it. I will just write this out as disubs. So it's got two C neighbors. And that is nice. It would be better to have 4 or 3, but having 2 carbon neighbors is better than having 1 or 0. So let's look at this product up at the top. I drew in my carbon, when we look at this alkene, it has 4 direct substituents, 2 on each side. But in this case, 1 of them is a carbon and 3 of them are hydrogens. So therefore, this guy would be a monosubstituted alkene because it only has 1 carbon neighbor. The one with 2 carbon neighbors is more stable. The one with only 1 carbon neighbors is less stable. And therefore, this guy down here would be the major product. You would get a lot more of this because it is a more stable product, and you would get less of this guy because it is less stable. All right, so unfortunately, unlike SN2, E2 gives you multiple products, but E1 would give you even more possible products. So take a break and run around if you need to, and come back and we will go into E1. Okay, so we're presented with another reaction here. We have an alkyl halide, and the alkyl halide can do either substitution or elimination. And in this case, what we're reacting it with is water. Water is a weak nucleophile, and it is also a weak base. So water is not going to be strong enough in order to do E2. So we can't do E2 with a weak base, so therefore we must do that E1 reaction. In the E1 reaction, the base doesn't just grab the hydrogen next to the alkyl halide. Instead, it just sits there and waits. And what we're waiting for is the leaving group to leave. And if the leaving group leaves, you would get, I'm going to draw all of this out. I know it's a pain, but with Lewis structures, you can really see where everything is, which is the best for reactions. And I'll just write some CH3s up there. All right, and so we would get this carbocation. But remember, anytime you can get a carbocation, you can also possibly get rearrangement. So let's look at the alternative situation, which is that that leaving group could leave, which would create a secondary carbocation. We can see that on the right side, we've created a secondary carbocation. But notice that you have a tertiary carbon next door. So you could simultaneously get rearrangement. And the only rearrangement that we're going to worry about is a hydride shift. This would give us a new possible carbocation that would have a CH3, CH2, and that hydride would shift over to this carbon, the third one down. Therefore, we would get our carbocation in this spot right here, which would make it tertiary. All right, once again, hydride shifts only happen if they can make the carbocation more stable. Since by default we got a secondary carbocation, we want to look for the possibility of a hydride shift giving us a tertiary. Well, we can't shift this guy over because that would just give us a different secondary carbocation. So there's no reason for that to occur, so it won't. But this is a carbocation, or this is a carbon next door that's tertiary, so we can get that shift. So just like SN1, all of this is the exact same thing as SN1. We will have 2 different possible carbocations. But with elimination, you can get multiple products from each of those. I know, I hear you sighing in the background. So let's see what we can do. I'm going to have to get a lot of colors for this one. Our water can grab a hydrogen next to our electrophile and form this alkene. And I'm going to condense this a little bit. That would give us this product. All right, let's switch it up a little bit. Our water could also pull a hydrogen off over here because this is a different CH right next to our electrophile. And that would give us another product that would be CH3, CH2, CH2, and then our carbon would have a double bond down here. All right, these hydrogens up here are also acidic, but the deal is that making a double bond here, making a double bond here would be exactly the same molecule, so we don't have to do all of them. Hopefully you can see why that is. If you're not sure, just ask me in class. All right, so that's all the products that we can get from this intermediate. Now we have to figure out the products we can get from this intermediate. So let's bust out some more colors. Our water, which is a weak base, can pull a hydrogen off of a carbon next to your electrophile. So we can grab that hydrogen and make an alkene over here, which would give us CH3 and an alkene between that second and third carbon. And then this guy would be left over there. All right, and we've got one more to go. We'll do this one in yellow. All right, and so the final thing we could possibly do is pull the hydrogen off of this side. But again, this is just a CH next to your C+, and that would give me CH3, CH2, and this third carbon over would make a bond to that fourth carbon. Whew. So, whenever you have E1, you could do rearrangement. If you do rearrangement, it gives you multiple carbocations, and then you can do elimination of your multiple carbocations to get multiple products of each, so you end up with multiple times multiple final products. You don't have to do deprotonation, because what will happen to all of those waters is they just become H3O+, and basically they're just lowering the pH of the solution a little bit. All right, if we look at these guys, we'll notice though that two of them are the same. This guy right here and this guy right here are actually the same. So therefore, we're only getting 3 overall products. 1, 2, and then both of these guys are the same third product. Only 3 products. But just like SN1, E1 is a pain. It gives you huge amounts of products, and so it never should be our first option. We always want to steer towards E2 if we want to do elimination. We always want to steer towards SN2 if we do substitution. And the reason for that practically is you want to have as few products as possible. All right, so please practice this. Once again, I'm going to give you a problem. I would ask you to get out some notes and take your time and look at all of the possible products you can form of this elimination reaction. Whew, thank you very much. I will see you in class.